Hi, I'm Colin. In this module, we're going to see how we can use the quotient rule for differentiation to differentiate the trigonometric function y equals tan x. Our goal is to show that the derivative of the function tan x is the function 1 on cosine x all squared. In other words, the function 1 on cos x all squared tells you how steep the tangent function is at every x value. Another quick observation, if I may. Notice that the derivative will not be defined whenever cosine x is 0. This occurs precisely when x is pi on 2, 3 pi on 2, 5 pi on 2, and etc., along with when x is negative pi on 2, negative 3 pi on 2, negative 5 pi on 2, and etc. That's because the graph of tan x has vertical asymptotes at those x values. You should revise the cosine and tan functions if you're a little rusty with these properties. Alright, let's now find a way to differentiate tan x. To do this, recall that for all x, tan x is just the function sine x on the function cosine x. This is an important trigonometric identity and shows that the tan function can just be synthesized from the basic functions sine and cosine. Now, since sine x and cosine x is just one function divided by another, in other words, the quotient of one function and another, it is an example of what we call a quotient function. And importantly, to differentiate quotient functions, we use an important formula called the quotient rule. The rule states the following. If I have a function, which I'll call u, divided by a function which I'll call v, then the derivative of this quotient function is given by the following lingo. vu dash minus uv dash all over v squared. In other words, if u is regarded as the function on top, and v is the function on the bottom, then the quotient rule states that the derivative is the bottom function times the derivative of the top one minus the top function times the derivative of the bottom one, all over the bottom function squared. Thus, here, the derivative of tan x, which is the same as the derivative of the quotient function, sine x on cosine x, can therefore be differentiated using the quotient rule. Labeling the top function sine to be u, and the bottom function cosine to be v, the quotient rule says that the derivative is, first and foremost, the bottom function v, which is cosine x, times the derivative of the top function u, that is, the derivative of sine x, minus the top function u, that's just sine x, times the derivative of the bottom function v, that is, the derivative of cos. And all of this is over the bottom function v all squared, that is, cos x all squared. Now recall that the derivative of sine is just cosine, and the derivative of cosine is negative sine. Thus our derivative is just cos x times cos x, which is cos x all squared, minus sine x times minus sine x, which is positive sine x all squared. And this is all over cosine x all squared. Now, looking at the numerator, Let's recall a very special identity from trigonometry that states for any angle x, cosine x all squared plus sine x all squared is always 1. This identity follows easily from the unit circle definition of cos and sine, along with Pythagoras' theorem. Thus, the derivative simplifies to just 1 on cos x all squared, which is what we will require to show. Now, the show is not over just yet. Let me take things a little further. Using an index law, I can write 1 on cosine x all squared as the square of 1 on cosine x. Now, the quotient function 1 on cosine x turned out to be so useful that mathematicians gave it its own name, the secant function, written as sec x. Thus, in conclusion, the derivative of the tan function can be regarded as either the function 1 on cos x all squared, or the square of the sec function. Alright, I hope you found that useful. See you next time.